All right, had a couple of issues getting the stream to start for some reason. Maybe there's some sort of rule about streaming that I don't know about on YouTube, but I guess we'll find that out the hard way if we find out at all. Also, you may have noticed the audio quality is better, at least I hope it is, because yesterday I looked through the, what do you call it? I guess the recording of the stream, and for whatever reason, my microphone didn't sound as good as I'm used to it sounding. And yeah, I figured out what the issue was, and hopefully it's fixed. But I guess I'll find out after this stream is done and I go and check the recording. Anyway, that's enough of me rambling. Let's go ahead and get started. So, our next topic for calculus, and yeah, we'll be doing calculus again today in case you didn't read the description. More calculus. Probably tomorrow is going to be physics, mechanics, both algebra based and calculus based. So your physics 1, physics C students, tomorrow's your day. But anyway, so our next topic in calculus, at least the next one I highlighted and thought was worth reviewing, is areas between curves. So let's go ahead and look at some examples of that. What to pick, what to pick, what to pick. Well, first I have a couple of problems here saying find the area of the shaded region. Let's do... I think I want to do the third one I'm seeing. So it has one curve that kind of looks like this, and it's described as x equals y squared minus 1. And then there's another curve that looks like this, and it's described as x equals square root of y. And then we've got the line y equals 1. And I guess this isn't drawn to scale, but there's the line y equals 1. So that's your y equals 1 line. And we want to find the area of the region they shaded, and their shading is over here. This is what they've shaded. Okay, so there's two ways we could do this. We could calculate the area of this region, the area between y equals 1 and x equals square root y, in one integral, and then in another integral we could calculate the area under x equals y squared minus 1 from this point to this point, and just add those two areas up. Or probably the easiest way, if you want to do it all in one integral, is to integrate in terms of y, in which case we would be integrating from, it looks like y equals 0 to y equals 1. And yeah, we would be integrating, I guess, horizontally in that case. So let's do the horizontal case. Or maybe I'll do both cases. Well, I'll decide later, but let's do the horizontal case first. So let's see. It's going to have to be right minus left so that we can get a positive value. Negative area doesn't make sense here, not in this context. So, well, I guess they've already done the work for us. The rightmost curve is x equals square root of y, and the leftmost curve is x equals y squared minus 1. So square root of y minus y squared minus 1. That's going to be the distance between the two curves, and then we're going to integrate that with respect to y from, it looks like 0 to 1. Okay, that doesn't look too bad. So I guess let's go ahead and integrate it. Integral of y to the 1/2 is going to be 2/3 y to the 3/2. And then I guess if I mentally distribute the minus, negative y squared would integrate to negative 1/3 y cubed. And then minus negative 1 is plus 1. Integrating that would give us plus y. And then that's evaluated from 0 to 1. If you plug in 0 for all of these, you get 0. So really we're just plugging in 1 here. 2/3 of 1 to the 3/2 minus 1/3 of 1 cubed plus 1 minus 2/3 of 0 to the 3/2 minus 1/3 of 0 cubed plus 0. That's not going to add anything, so 2/3 minus 1/3 plus 1. 2/3 minus 1/3 is 1/3 plus 1 is equal to 4/3. Okay, that wasn't too bad. Let's go ahead and see if we get the same result if we split it into two integrals and integrate vertically like we're used to. What if we integrated like this, where we calculated that region first and then calculated that region? Well, it doesn't matter which one we do first, but the point is we calculate them separately and then we add them. Let's go ahead and see. We should be getting the same result. So from here to here, the top curve is x equals y squared minus 1. I want to rewrite that in terms of y, or no, in terms of x. I want to solve it for y in terms of x. And our bottom curve then would be just the line y equals 0. Then from here to here, I guess we'd have to figure out where that point is. Well, it's not too hard to find out. I believe that's going to be at 1, 1, right? Because it's on y equals 1 and then x equals square root of y, so square root of 1, yeah. So definitely not drawn to scale, because if it was, it would look more like a square than a rectangle. But yeah, so it looks like the upper curve is going to be y equals 1 from 0 to 1. And then the lower curve is going to be x equals square root y, which can be rewritten as y equals x squared. Okay, let's organize all that information because I am kind of going all over the place here. So this can be written as y equals x squared. That's this curve. X equals y squared minus 1. Add the 1 and take the square root, and you would get y equals the square root of x plus 1. That would be this curve over here. And then this point right here, where y is equal to 0, that would mean x would have to be negative 1. This is at x equals negative 1. Okay, so what we have is an integral from negative 1 to 0 of, let's see, top curve minus bottom curve. It would be root of x plus 1 minus 0. So I guess I'm not going to write anything there. And then integrated with respect to x. Plus, then we have a separate integral here. From 0 to 1, the top and bottom curves have changed. From 0 to positive 1, the top curve is 1 minus the bottom curve is going to be y equals x squared. And integrated with respect to x. So let's see. Integral of square root of x plus 1. So if we did a u substitution using u equals x plus 1, du equals dx, and ultimately we would treat it the same way we treated square root of x. So integral of x plus 1 to the 1/2 is just going to become x plus 1 to the 3/2 divided by 3/2, or times 2/3, and that's evaluated from -1 to 0, plus integral from 0 to 1, this one's going to be easy, x minus 1/3 x cubed, evaluated from 0 to 1. Okay, from -1 to 0, so if I plug in a 0 here, I would get 0 plus 1 is 1 to the 3/2 is 1 times 2/3 is 2/3. I guess I'll write that up here. So we got 2/3 minus, if we plug in -1, -1 plus 1 is 0, so that's 0. Okay, so that takes care of the first integral. Plus, for x minus 1/3 x cubed, 1 minus 1/3 of 1 cubed is just going to be 2/3. Minus, if I plug in 0, that's just 0. And we get 2/3 plus 2/3, which is equal to 4/3. Same as what we got before. So yeah, both methods work, but one method is definitely more convenient. Okay, let's take a look at another case. So we've got another drawing they have for us. They've drawn another curve for us here, and what do we have? We have a pair of parabolas. One looks like this, going through the origin and curving back like that. And then the other one goes, well, it also goes through the origin. But it kind of goes something like this. And yeah, I didn't draw that too symmetrically, but they are supposed to be parabolas. They've marked this point for us as -3, 3. And of course, this is the origin, so that's just 0, 0. And then they've told us that this curve is x equals y squared minus 4y. Y squared minus 4y. While this curve is x equals 2y minus y squared. X equals 2y minus y squared. Okay. So, since they've set it up for us as x in terms of y, they're suggesting to us that we should just integrate horizontally, which wouldn't be a bad idea, because if you want to integrate vertically, you would actually have to split this up into two integrals, because over here, over here, your top curve is half of y squared minus 4y, the top half of that parabola, and then your bottom curve is the bottom half of that same parabola. So, I mean, I guess you could do it, but it just doesn't feel very practical. Then you've got over here, at this point, it looks like your top curve is 2y minus y squared, while your bottom curve is y squared minus 4y. And then over here, it's basically a reversal of that first scenario, where the top curve is the top half of 2y minus y squared, and your bottom curve is the bottom half of 2y minus y squared. So you'd have to split it up into 3 separate integrals if you wanted to do it vertically, and you would have to take 2 of your curves and actually split them into 2 equations, one for the top half and one for the bottom half. Not worth it. It's easier to integrate horizontally because horizontally the left curve is always the x equals y squared minus 4y curve, while the right curve is always 2y minus y squared. X equals 2y minus y squared. Of course, you probably already knew that that was the thing to do, but, you know, it's always good to look at it and consider our options and see why we do things the way we do, rather than just because my teacher said so. I would hope students have developed a higher level of critical thinking than that. But then again, given some of the cases I've had to work with, it doesn't seem like our education system is really built to produce that kind of thinking in students. But enough of me rambling. Let's actually do this thing. So I want to do right minus left because the further to the right the curve is, the more positive its values are. Positive minus less positive or negative would result in a positive. So where are we integrating to and from? It looks like we're integrating with respect to y. So we're going from y equals 0 to y equals 3. And then we're doing x right minus x left. So 2y minus y squared is further to the right, at least for the section we're concerned with, minus y squared minus 4y. Whoops. Thinking ahead here, maybe too far ahead. Let's distribute that minus sign, so integral from 0 to 3 of 2y minus y squared minus y squared plus 4y. Oh, this makes things easier. Or does it? No. I thought the y squareds were going to cancel out. Spoke too soon. 0 to 3 of, let's see, 2y plus 4y is 6y. And then that's negative 2y squared dy. Pretty simple. It's just a polynomial. Nothing too fancy going on here. So 6y, so that's going to become 6y squared over 2, 3y squared, minus, that's going to become 2/3 y cubed, evaluated from 0 to 3. Plugging in 3, we get 3 times 3 squared minus 2/3 of 3 cubed, and then minus 3 times 0 squared minus 2/3 of 0 cubed. Okay, the zeros give us nothing. No surprise there. And then that's going to give us 27 minus 3 cubed is also 27. 2/3 of 27 would be 18. So 27 minus 2/3 of 27 is 1/3 of 27 is 9 is another way you could think about it. But yeah, there we go. We've got an area of 9. Okay, so those are cases where the curves are drawn for us. Let's take a look at a case where they don't make it so easy for us. What to pick, what to pick. this one looks like it might be interesting. So we've got cosine of pi x and 4x squared minus 1 for two of our curves. Let's see if I can at least fit the beginning of this problem in here. So they want the region enclosed by y equals, where did it go? Cosine of pi x and y equals 4x squared minus 1. Okay, probably a good idea to sketch the curves so we can get a sense of how they work. I want to start with 4x squared minus 1, so that's going to have an intercept at -1. Let's draw that here. And then 4x squared, so it's going to be taller and thinner than your standard x squared graph. And let me draw it in a different color. Okay, so something like that. And I guess I'm going to want to, well, we'll see whether or not I actually want to solve for those intersection points. What about cosine of pi x? What about cosine of pi x? Oh, well, I guess it's not too hard to get those intersection points after all. 4x squared minus 1, set it equal to 0. We get 1 equals 4x squared, which gives us 1/4 equals x squared, so x squared is plus or minus 1/2. Don't know if these will be relevant points, but there they are just in case. Cosine of pi x. So let's see, where does cosine hit 0? Normally it hits 0 at pi over 2 and 3 pi over 2 and negative pi over 2 and so on. But in this case, since it's pi x, it's going to hit 0 at, well, you get pi over 2 when x is equal to 1/2, and you get negative pi over 2 when x is equal to -1/2. Okay, I think I see where this is going. And then, of course, it's supposed to peak at 1, so I've already drawn this poorly. At least if I'm trying to draw it to scale, I have. Okay, and then the rest of it just kind of continues on like that. Okay, so it looks like we've found our region of interest. There's only one area between those curves, and that's this area right here. And it looks like integrating vertically makes the most sense, so integral of top curve minus bottom curve, and it looks like it's from -1/2 to +1/2. Okay, so let's see, integral from -1/2 to +1/2 of cosine of pi x is our top curve in this case, minus 4x squared minus 1. I'm going to go ahead and distribute the negative sign, so that's minus 4x squared and plus 1. And of course, we're integrating with respect to x. We're adding a bunch of vertical strips that are stacked horizontally from left to right. Okay. And I guess the rest is pretty simple from there. I would hope that you don't need to use u substitution to get the integral of cosine pi x, but if you have to, you can do u equals pi x to just solve the integral of cosine pi x on its lonesome. That being said, I would hope that most students watching this have already noticed a pattern in integrating things like e to the k times x sine or cosine of k times x, where k is a constant, of course. I would hope that students have already noticed a simple pattern that they can take advantage of so that they don't have to waste time u substituting each time they see one of these. But yeah, if you don't know about that pattern, try integrating each of these using u substitution and see if you can derive a rule for their integrals. It will definitely save you a ton of time, so it's worth it. But yeah, integral of cosine pi x is going to be sine of pi x over pi. 1 over pi times sine of pi x. And then that's going to be minus 4/3 x cubed. And then that's going to be plus x. And that's going to be evaluated from negative 1/2 to positive 1/2. Or we can evaluate it from 0 to 1/2 and multiply that by 2. Because this integrand right here, and if you haven't heard the word integrand before, that just means the thing inside of the integral. This integrand right here is even. This is an even function. Cosine is an even function. X squared, that's an even function. And constants are even functions because you can think of them as 0-degree polynomials, where 0, of course, is an even number. So yeah, the sums and differences of even functions are themselves even functions. So yeah, I'm going to rewrite this and say it's 2 times, where am I going to fit this? New sheet. So I'm going to say it's going to be equal to 2 times 1 over pi sine of pi x minus 4/3 x cubed plus x, evaluated from 0 to 1/2. And if I do that, then there's nothing to subtract because sine of pi times 0 is 0, and plugging 0 into a polynomial is going to be 0. So nothing to subtract. All we have to do is plug in 1/2. So it's going to be 2 over pi, multiplying the 2 and the 1 over pi there, sine of pi times 1/2. So that's sine of pi over 2, which is 1. Oh, wait a minute. No. What am I doing? Do not multiply the 2. I just realized that's a bad idea. Okay. Let's start again over here. 2 times 1 over pi times sine of pi times 1/2, as we said, was 1, minus 4/3 of 1/2 cubed. 1/2 cubed is an eighth. 4 over 8 reduces to 1 over 2, and then you've got the 3, so that's 1/6 plus 1/2, or 3/6 in other words. 1/6 plus 3/6 is going to reduce to 2/3. So we've got 2 times 1 over pi. Oh, wait, did I add? No, it's supposed to be subtraction. Subtracting 1/2, or subtracting 1/6 from 1/2 is going to be 2/6 or 1/3. Okay. Getting a little hasty there. 2 over pi minus 2/3. Is that even going to be positive? It doesn't look like it. What did I do wrong? Oh, it's plus 1/3. Okay. Yeah, negative 1/6, positive 1/2. Okay. Glad I did that check to see whether or not this actually comes out positive. See, there's no such thing as becoming a mathematician who never makes mistakes. I've had math professors I would know. They make mistakes all the time. If even the math professors are still making mistakes, that means the only way to deal with mistakes is to get better at catching them. And to get better at catching them, you just have to develop the habit of checking your results frequently and asking yourself, does my result make sense? If you're one of my regular students, you've probably heard me say that on numerous occasions, but if you're not, well, hopefully you've learned something new today about the value of mistake detection. Anyway, let's see whether or not there's another area between curves problem that's worth doing. There's one type specifically that I'm looking for. I don't know if I'll recognize it when I see it, though. Oh, I think I've found it. Well, not quite. But it gives me an idea. Actually, wait, does it work? Yeah, I guess technically it works. Okay, so they tell us to find the area between the curves y equals, I'm going to modify it. I'm going to make it y equals x cubed minus x. Well, should I? No, I think it'll work fine as is. Okay. They want it between y equals x cubed and the line y equals x. Let's draw that and see what we're looking at. What is the area enclosed between those two curves? Y equals x is easy enough to draw. And y equals x cubed is a classic. We should know how to draw that. And there we have it. Well, I guess I kind of drew that more like a tangent curve. It should slant more to the left and right. Yeah, something like that. Okay, so the area enclosed between these two curves, there's actually two areas. We've got one over here and one over here. So technically we have to split this up into two integrals. And it looks like we're going to integrate vertical strips. Well, actually it seems like it would be equally easy whether you did it vertically or horizontally. But since we've got our equations as y in terms of x, it just makes sense to do it with vertical strips. Yeah, we'll integrate with respect to x. So technically, you'd want to split this into two integrals, but because of the symmetry, we only have to do one integral and multiply it by 2. I don't think it's hard to see why these two regions have equal area. But let's see, so assuming we didn't know that, why would we have to split it up into two integrals? Because the top curve and bottom curve, or left curve and right curve if you're doing it with horizontal strips, is going to change once you hit the origin. Before hitting the origin, to the left of the origin, your left curve is the cubic function and your right curve is the linear function. Or in terms of vertical strips, your top function is the cubic, and your bottom function is the line. Whereas after the origin, your top function is the line and your bottom is the cubic. Or in terms of horizontal strips, your right function is the cubic and your left is the line. So that's why you'd have to split it up into two integrals, because your top and bottom, or left and right curves, swap places. But You can set that up for yourself. I'm just going to take the shortcut I described earlier, so I'm just going to do this part. So where do those two curves intersect? Where does y equals x cubed touch y equals x? When they equal each other. So when does x cubed equal x? Both at -1 and at +1. At x equals -1 and at x equals +1. Let's see. And I guess if you wanted to show the work for that on the exam, you would do intersection occurs where the first y is equal to the second y, x cubed is equal to x, and then you would subtract the x on both sides and get x cubed minus x equals 0, factor out an x, and then you'd get x squared minus 1, and then you can factor that further and get x plus 1 times x minus 1 is equal to 0. And that gives you three possibilities: x equals 0, x equals -1, and x equals 1 for the intersection points. But that's if you wanted to show the work. I'm sure most people can tell just by eyeballing it. But there's the work in case you weren't sure how to do it. I would hope this would be the least of your problems if you're taking calculus, but I've had students who somehow got into calculus even though they didn't develop their algebra skills all that well, and I'm not sure who deserves the blame when it comes to scenarios like that, because sometimes there are schools that just kind of try to pump students into AP courses and, you know, I guess, is throw them for the wolves the right term? I don't know. They just kind of throw them in there and whatever happens, happens. Which I think is kind of irresponsible, but some would argue that it's an interesting and novel teaching philosophy. We'll probably have a video of me rambling about that someday. Not making any promises, but knowing me, I'd probably end up talking about it at some point anyway. Let's get back to our problem. So 2 times integral from, I'm just going to do it from 0 to 1. You could also do it from -1 to 0, but why risk it? Negatives can easily be missed. They're very mistake prone. Integral from 0 to 1 of top curve minus bottom curve. In this case, the top curve is y equals x, minus the bottom curve is x cubed dx. And the rest is history. You know how to integrate a polynomial. So that's where I'm stopping for that problem. Let's move on to a new topic. Volumes. Let's take a look at all of our different volumes. Discs, washers, and cross sections. So let's start with a warm-up. Let's do y equals the square root of x minus 1. Should I do this on this page? Yeah. Well, we'll start it on this page, and if there's not enough room, we'll continue elsewhere. So we've got y equals the square root of x minus 1. Y equals the square root of x minus 1. And it looks like our other boundary is y equals 0, and one more boundary we have is x equals 5. So those are the bounds of our region in question. And we are rotating around the x-axis. Rotating around the x-axis. Okay. This shouldn't be too hard. Let's go ahead and draw to make sure we understand what it is we're looking at. Okay, y equals square root of x minus 1. Looks like square root of x, but shifted to the right one space. So that would look like this. And that's at x equals 1. Okay, and then we've got the y equals 0 line is a boundary. And then we've got x equals 5 is a boundary. We'll pretend that this is where 5 is, though that doesn't look like it's to scale. But yeah, there's x equals 5. Okay, and it looks like this is our region of interest. And we're rotating it around the x-axis, which will result in a shape that kind of looks like a bowl. Which will result in a shape that kind of looks like a bowl. I don't even know if that looks very 3D. But yeah, that's what we're trying to do. So it looks like we're just making solid disks. There are no gaps in between the rotated curve and the x-axis, or I should say the rotated region and the x-axis. No gaps between them, so yeah, no subtraction needed. It's disks, not washers. Okay, so we're going to be integrating a bunch of these disks. They look something like this. And we're just stacking a whole bunch of them on top of each other. Like so. And if you make the disks thin enough and you stack a whole bunch of them, then they will put together some sort of smooth, solid object. Okay, so what is the volume of each individual disk? You've probably memorized the formula. I'm going to insist that you make sure you understand the geometry. If you understand the geometry, you don't need to memorize the formulas. If you understand the geometry, it actually gives you more flexibility because then you can handle scenarios that you might not have been given equations for, because you'll be able to construct your own equations. Okay, so each disk is going to have a radius. Each disk is going to have some radius, let's call it r, and the volume of each disk, if you think about it as a cylinder, it's going to have the area of the base is pi r squared. So volume of a disk, I'm just going to call it dV. Well, we'll worry about that later. So volume of an individual disk is equal to the area of the base of an individual disk, so that's pi r squared, times the height of the disk, which in this case the height is determined by the change in x. So times delta x of the disk. If we make them super thin, then we're talking about an infinitesimally small volume of an individual disk, or what we would call dV of the disk, is equal to pi r squared times a really, really tiny change in x. These are supposed to be super thin disks. You can think of dx as what delta x would be if it approached 0. Okay, and there we go. So the total volume then would be the integral of each of the individual slices of volume, which would be the integral of pi r squared dx. Okay, so our volume is equal to integral of pi times the radius squared times dx. What is the radius? Well, it looks like all of our disks are going to be centered on the x-axis for this problem. And so for each and every individual disk, its radius is just going to be the distance from the center, our x-axis, to the rim of the disk, which is always going to be touching this curve. Therefore, the radius is the distance from this curve to the x-axis, so square root of x minus 1 minus 0. So square root of x minus 1, and then that's the radius. We want the radius squared and integrated with respect to x. Okay, and we're integrating, it looks like, from x equals 1 to x equals 5. So that's going to be the integral, I'll factor out the pi, integral from 1 to 5 of, if we square a square root, we just get whatever was inside the square root, and we're integrating that with respect to x, so that's going to be 1/2 x squared minus x. Let's continue that on our next page. Let me see, so it's going to be pi times 1/2 x squared minus x evaluated from 1 to 5, which is equal to pi times, let's see, I'm going to do things a little bit differently from how I've been doing them before. I'm sure many of you have noticed that you can actually do this, but for those who haven't, this might blow your minds a bit, or confuse you and make you angry that it's not the way your teacher taught you to do it. Can't win them all. So I'm going to do 1/2, it looks like that's going to be 5 squared minus 1 squared, minus x is just going to be, let's see, 5 minus 1. And close those brackets. Okay, 5 squared minus 1 squared is 25 minus 1 is 24. Half of 24 is 12. 5 minus 1 is 4, so we've got 12 minus 4 is 8. So that looks like it's going to be 8 pi. For those confused by what I just did over there, it's really not that hard to show what I did is equivalent to what we would normally do. Normally, what we would do is pi times, and then in the brackets we would do 1/2 5 squared minus 5, right? 1/2 x squared minus x, and then that minus, and then that minus 1/2 1 squared minus 1. I guess I should put parentheses around that 5 there. And yeah, if you, I wouldn't call it combining like terms per se, but if you put these terms together, if you group these terms together and you group these terms together, then I think you can see why 1/2 5 squared minus 1/2 1 squared becomes 1/2 of 5 squared minus 1 squared, and then similar reasoning applies to the 5 and the 1 over there. If you don't get it, just stick to doing things the normal way, but if you do get it, that can actually save you considerable amount of time if you evaluate your definite integrals that way. Anyway, that's it for that problem. All this for a warm-up. What should we pick next? How about number 10? Looks interesting to me. So what number 10 says is that we've got y equals 1/4 x squared we've also got x equals 2 and y equals 0. X equals 2 and y equals 0. Okay, let's go ahead and draw the graph to see what we're looking at. So 1/4 x squared One-fourth x squared, well, it would be 0 at x equals 0. I know that much. And I guess it would be wider than normal because its coefficient has a magnitude less than 1. You learned that stuff in pre-calculus. Just saying, it was called pre-calculus for a reason. And then x equals 2 would be... Oh, let's see. So x equals 2. If I plug in 2 into y equals 1/4 x squared, that's going to give us 1. Okay, I think that might be relevant. Let's mark it... Oh, how about here? That looks about right. So at x equals 2, and I'm going to write it off to the side so I can actually draw the line x equals 2 there. And then we've got y equals 0 is our final boundary. And so it wants the region that's bounded between all three of those. So it has to touch all three. Well, the only region that fits that description would be this one right here. This one right here is the only one that fits. It's touching 1/4 x squared, it's touching x equals 2, and it's touching y equals 0. It's the only one that works. Oh, and I forgot to write, they said it was rotated around the y-axis. Rotated around the y-axis. Rotated around the y-axis. Okay, so it's being rotated like so. Interesting. So it looks like we're going to have a big hole in this shape. It looks like this calls for using washers. Okay, so with washers, it's pretty much the same thing as discs, except there's an outer disc, which is if you treated it like the standard disc method, and then there's inner discs, which are really holes that are shaped like discs that you need to subtract out of the outer disc. That's really all there is to it. So we're going to have discs that look like... We're going to have discs that look like so. We're going to have something that looks like this, and then in the middle, there's going to be a disc-shaped hole. And I guess I'll draw a dotted line representing the bottom of the hole. So yeah, that's all there is to it. So our volume pieces are just going to be the volume of the outer disk minus the volume of the disc-shaped hole. We've got, it looks like the radius of each outer disk is just going to go from the y-axis all the way to the x equals 2 line for every point in this region. So it looks like our outer radius is going to be from x equals 0 to x equals 2 is just a constant 2. And it looks like our inner radius is going to be the distance from the y-axis to the curve. The distance from the y-axis to that curve. I probably should not have done that in red. But the distance from the y-axis to the curve, so the y-axis is at x equals 0. The curve is at... Yeah, I want to write this in terms of x because it's a horizontal distance. So let's rearrange y equals 1/4 x squared. Multiplying by 4 gives us 4y equals x squared. And then taking the square root, x equals square root of 4 is 2, and then that's 2 root y. Okay, so it looks like our inner radius is 2 root y minus 0. X equals 2 root y minus x equals 0. All right, and that takes care of that. So the volume of the outer disk, is going to be pi times r outer squared times, I guess in this case the height would be a change in y, so that's delta y. Volume of the inner disk, similar pattern, pi times radius inner squared times the same delta y. And of course, if we want to calculate this, well, if we want to put this in calculus terms, if we want to make these super thin washers, then our delta y becomes a dy, and our v's become dv's, and our total volume is the outer volume minus the whole, so v outer minus v inner, or dv outer minus dv inner, gives us dv total equals pi times r outer squared times dy minus pi times r inner squared times dy. Factoring out the pi, we've got r outer squared minus r inner squared, also factoring out the dy, leaving it out like that. That should do it. So let's see here. I can pull the pi out of the integral. I can substitute r outer and r inner. Want to make sure they're written in terms of y, which we've already done. So our volume is equal to... Oh, and what are our integration bounds? Well, if we're integrating in terms of y, we're going from y equals 0 to y equals 1. As I highlighted earlier, that's where this intersection point happens. Where x is equal to 2, y is equal to 1, that's the highest y we get. So y goes from 0 to 1, factor out the pi, and r outer squared is 2 squared, which is 4, minus r inner squared is the square of 2 root y, which is 4y. And integrate with respect to y. And then from there, you know what to do. It's just a polynomial, not too hard to integrate. Let's take a look at another. Let's see if we have something rotated around a different axis. This one might be good. So we're given bounds of y equals x squared and y equals 4. And we're rotating around the y equals 4 line. Oh, wait, that's... Okay, let's do it anyway. Feels like it's simpler than what I was expecting, but let's do it anyway. So if I go ahead and draw my region, let's do that over here. We've got y equals x squared, which is going to look like this classic parabola. We've got y equals 4, which will occur around here. So that's at y equals 4. And yeah, we're rotating this around y equals 4. Let me get those intersection points first. So when y equals 4, 4 equals x squared, meaning x is plus or minus 2. And that takes care of that. And we're rotating this thing around the y equals 4 axis. So this is our region, of course. And we're rotating it. I guess I'll do it in orange. We're rotating it like this. And I guess I didn't really leave enough room to show that central disk. But yeah, this is essentially what we're looking at. Okay, so nothing really changes if you understand geometrically what we're doing. We're still integrating pi times the radius squared times a small change in either x or y. And I guess the way I've drawn it, it looks like the heights of our disks are going to be parallel to the x-axis, so it looks like a small change in x will give the height of each cylinder. But yeah, that part doesn't change. The individual volume pieces are still pi times the radius squared times a change in x or y. In this case, it's a small change in x. The only thing that's changed is how you would actually calculate the radius. So in this case, the radius is not equal to the value of the function at any given point. The radius is the distance between this line and the curve beneath it. And that's not too hard to calculate. How do I get, say, this distance right here? All I have to do is calculate the y-coordinate of the top minus the y-coordinate of the bottom. So it's top curve minus bottom curve. 4 minus x squared. Okay, so radius is equal to 4 minus x squared. Whatever the x is, I can calculate the radius for that particular x. And the rest is history. So we're integrating, it looks like, from -2 to 2. Volume equals integral from -2 to 2. And I guess because of symmetry, you can just do it from 0 to 2 and multiply by 2. But it's the integral from -2 to 2 of pi times 4 minus x squared dx. You know how to FOIL, you know how to integrate the resulting polynomial, and I guess you can take it from there. Let's take a look at another case. There's one case that I'm still waiting for that hasn't shown up. Well, actually, I guess this kind of counts. You know what? Yeah. What if I made a modified version of this? What if I had almost the same exact setup, except the axis of rotation was different. Y equals x squared, y equals 4. And then the axis of rotation, let's have that be the y equals 7 line. Let's say that was my axis of rotation. Okay, what happens then? If I rotate around y equals 7, how does that change things? So let me draw this scenario again. That looks good. Then we've got our y equals 4 should be about here. So that's our y equals 4 line. And then our y equals 7 line is going to be our axis of rotation. Let's say that's around here. So that's y equals 7. Okay. How does this change things? And I guess I should mark the -2 and the 2 again. Okay, how does this change things? Well, now that we're rotating around this axis, we actually have an inner radius and an outer radius. We've got a hole in the middle, since this is our region of interest. It hasn't changed. Let me shade it, and I guess that means I can't use orange anymore for showing our disks. But yeah, so you've got your inner disks, which are just holes, and you've got your outer disks, looking something like that. So now we have an inner radius and an outer radius to calculate. So now our dv is going to be a pi r outer squared minus pi r inner squared times dx. Pi r out squared minus r in squared dx. Okay, our outer radius is just going to be the distance from y equals 7 to wherever this curve is at any given x. So it's the distance from y equals 7 to y equals x squared, in other words. R outer is the distance from y equals 7 to y equals x squared for any given x. That's just a vertical distance, so you can just subtract the y values. A y value of x squared minus a y value of 7, or a y value of 7 minus a y value of x squared. Technically, you don't have to do top minus bottom here, because whatever your outer radius is, you're going to square it, and any number that you square becomes positive. But I guess just for the sake of comfort, I guess, we can rewrite it as 7 minus x squared. So absolute value of x squared minus 7, which is going to be 7 minus x squared. Okay, and the inner radius is, well, the inner radius is going to be constant, because at any given point, the distance from y equals 7 to the inner part of our object, it's just from y equals 7 to y equals 4. It's just a constant 3. Okay, and from there, I guess I'll just set up the integral, but not solve it, and that'll take care of that. So we would have volume equals the integral from, it's going to be from -2 to 2. And again, because of symmetry, you could also just do 2 times the integral from 0 to 2. That part hasn't changed here. But it's the integral from -2 to 2 of, let's see, I guess I'll factor out the pi. and then r outer squared, so 7 minus x squared minus r inner squared, which is just going to be 9, and then times dx. You know how to FOIL that. You know how to integrate a polynomial. The rest is on you. Okay, let's see if we can find a cross-sections problem in here. If not, I can always just make up my own. These are all symbolic problems. No numerical problems. It doesn't look like it. Oh well, nothing wrong with doing a symbolic cross-section problem, I suppose. So we've got a problem that says a frustum of a pyramid. A frustum of a pyramid. A frustum of a pyramid. Which is basically a pyramid with its top chopped off. A frustum of a pyramid with square base of side B and square top of side A and height of H. What happens if A equals B? What happens if A equals 0? What? Hold on. Is this part of like some bigger... For 47 through 59, find the volume of the described solid. Okay, so find the volume of a frustum of a pyramid with square base of side B and square top of side A and height H, and they've actually drawn it for us. So it looks like this. So the square top side length is A, and then it's got a square bottom. With a side length of B. And of course, if you want, you can draw the rest over there. I guess I drew that a bit poorly. I wanted the dotted lines to actually connect somewhere we could see them. But oh well. So yeah, how do we find the volume of this thing? Or at least, in this case, you can't actually find a volume, but you can derive a volume formula. And then, I guess, in a numerical problem, they'd just give you values for A and B to plug in. Which we don't have here, but that's okay. So, when I see this, I think of drawing an axis through the center of my pyramid. And let's see, I'm comfortable with lining this thing up against the, or along, I should say, the x-axis. So let's do that. Let's do that. So if my pyramid was aligned along my x-axis, then it looks like my pyramid is the result of taking a straight line through the origin. I guess it doesn't technically have to be through the origin, but through the origin makes it simple. So it's a straight line through the origin, and then we've got, I guess at some point over here, you would at some point over here you would cut it off, and then over here you'd cut it off to get the bottom of the pyramid. Are those A and B? No, those would be maybe half of A and half of B. Well, I guess it depends on the slant. Oh, and they told us that the height is h. So, I guess... Let's see. So the height is h. Maybe I'm just overthinking this. Okay, whatever this is and whatever this is, they're proportional to A and B. And in fact, they would actually be, so this would be, okay, so this would be half of B. I'll just call it B over 2. And that would be A over 2, which I can't really squeeze in there. Let me redraw this on a new sheet. So we would have, let's space them apart a little bit better here. So over here, this would be equal to half of A over 2, and this would be equal to half of B. This would be equal to B over 2. And let me see, I've got my ruler with me. Let's not screw this up. Okay, that looks good. And then this would represent the height of our pyramid. Okay, what can I do with that information? Can I derive some sort of formula for this line? It might take me a minute to see it, but there should be a way to write some sort of equation here. So I could do... Oh, yeah, I can calculate the slope. So it's going to be y2 minus y1 over x2 minus x1. Y2 minus y1 being the heights b over 2 and a over 2. B over 2 minus a over 2 over x2 minus x1. I don't know what they are, but I do know that the difference between them is going to have to be h. And so the slope of this red line is going to be, I'm going to factor out the 1/2 b minus a all over h. Okay, so that gives us a slope based on a bunch of constants that we don't know. And if we have it go through the origin, it has to go through the origin because that's the tip of the pyramid that this frustum was cut off of. So yeah, it has to reach it has to hit the origin at some point. I mean, if we make a symmetric drawing, I guess I'll draw a copy of a over 2 as a dotted line there and there. And yeah, we should be getting something like this. I guess I didn't draw that out far enough. Yeah, that looks right. Okay, so if I write my full equation of this red line, then all I have to do is, well, we've got the y-intercept is 0, so y equals mx plus b, y equals 1/2 b minus a over h times x plus b, where, not this b of course, but the b from the linear equation formula, the intercept is 0. So don't even bother writing it in the first place. Okay, so we've got ourselves an equation of a line. Now then, to get volume, what we would do is just take a bunch of cross sections. In this case, our cross sections would have to be squares. In this case, our cross sections would have to be squares, and the side lengths of those squares would have to be the distance between, the distance between this top line and this bottom line, or double the distance between the x-axis and the top line. So here's the full side length of any given square cross section. And yeah, we can just take the top half of each one, and in the end multiply everything by 2, and that'll save us the trouble of having to define this other line. Not that it would be too hard to do, it's the exact same thing, but with a negative sign. So this dotted line would be y equals negative 1/2 b minus a over h. Okay, that's not too bad. So yeah, imagine having a bunch of square pieces. I think I had like a square cutout that I was using for an example with a student last week. Or did I throw that away? I think I threw it away. Let me go and cut out a new one just to help illustrate what we're looking at. There's my scissors. And let's see. I guess I can cut out a piece of an index card. Let's see. So I want it to align with that. So let's mark here. And I'll try to get it as close to square shaped as possible, but whatever happens, happens. Okay, let's see. So yeah, that looks kind of square shaped. So yeah, we're stacking a bunch of squares like so along this pair of lines. And once you stack a whole bunch of them, you're going to get a pyramid, or at least in this case, a pyramid with its tip cut off. A frustum of a pyramid, as it's called in the problem. Okay, so that takes care of that. Maybe you didn't need that visual, but like I said earlier, if you understand the geometry, you do not need to memorize formulas. Anyway, our cross sections are squares, so let's go ahead and derive a volume formula for this thing. So for the volume of each individual square piece, remember these are not flat squares that we're working with. This frustum thing is a stack of square tiles. They have some thickness to them. You've got some sort of square tile at the bottom, I guess. And let's see, do I want to... Okay, before I shoot myself in the foot here, let me not draw this whole entire thing yet until I draw some more pieces stacked on top. Okay, there we go. Now it's coming together. I think my 3D drawing skills just leveled up today. Okay, something like this. We're stacking a bunch of square tiles like so. I think I messed that up. Okay, something like this. And you can imagine if you had a whole bunch of these and they were really thin, then you could make this frustum thing. If you slice this thing into super thin slices, then you'd basically have almost like a deck of cards. Okay, so imagine this, but rotate this picture 90 degrees, and that's what we're looking at over there. So for each of these square tiles, we've got the side length is just going to be 2 times the distance from y equals 0 to this line. So side length, I'll call it S, is 2 times the distance from the x-axis to the curve. That's just y of the curve minus y of the x-axis. That's just y of the curve, or I guess line, since y at the x-axis is 0. So that's 2 times 1/2 b minus a over h times x. And that's the side length of each individual square tile. Now then, if I know the side length of one such square tile, then I can calculate the area of its base, which would just be the side length squared. And then if I multiply that by the height or thickness, this thickness, I guess, would be, since they're stacked horizontally rather than vertically the way I've drawn them, this thickness would be a change in x, unless you make them super thin, in which case the thickness is dx. So the dv for an individual square tile is going to be s squared, the area of the base, times dx. That would give us a small slice of volume. Okay, so it looks like we are integrating from, I don't even know what those x values are, so I guess we need to determine those first. But we're integrating from somewhere to somewhere the square of our side length. So we're integrating, 2 times 1/2 cancels out, and so we're integrating b minus a over h times x, all squared, times dx. And what would our starting and ending values be? Well, now that we have this, we can solve for the 2 x's in this case. So if I plug in y equals a over 2, where should I do this? I'll do it down here. A over 2 is going to be our y, is equal to 1/2 times b minus a over h. I can cancel the 1/2, multiplying both sides by 2. And then a equals b minus a over h multiplied by h. we've got, oh, and I forgot the x. Okay. Multiply by h, and that would give us AH equals B minus A times x, divide by B minus A, and that would do it. So x over here, wow, this is more complicated than I was anticipating, but I guess that makes it a good practice problem. So it looks like our starting x is going to be, I guess I'll write it in green. Our starting x is AH over B minus A. And then we're integrating to, if I follow the same process I did here in pink, but instead of A over 2, I started with B over 2, then I would end up with BH over B minus A. I would end up with my top bound being BH over B minus A. And the way I've written that, it's probably not even legible anyway. But there you go, that's our volume formula. I think I want to actually work this one out and see what the result is. Let's see. We've got volume equals integral. Well, I'm gonna, hold on. Volume equals, I'm gonna factor out the square of B minus A over H. So B minus A over H, quantity squared. I am not going to FOIL this. I get the feeling that maybe something will simplify later. And if I FOIL now, I'm just going to needlessly complicate things. So we'll save the foiling for later, if at all. AH over B minus A and BH over B minus A. Still didn't create enough room for that. And then all that's left inside of our integrand would be x squared dx, which isn't too hard to determine. 1/3 x cubed. Oh goodness, this looks like it's going to be one terrifying algebraic monstrosity here. So it looks like we've got B minus A over H quantity squared, that's still out there. And then we've got 1/3, let's see, 1/3 x cubed, so it's going to be 1/3 BH over B minus A cubed minus 1/3 AH over B minus A cubed. Oh goodness. And then we've got, well, if I distribute a B minus A squared across these terms, then the B minus A cubed just becomes B minus A. And then if I distribute a 1 over H squared across these terms, then the H cubed is going to just become H. And that leaves us with a B cubed and an A cubed over there. And of course a single H and a single B minus A. Okay, so we would be left with, factor out the 1/3, and we would have, that's just going to become B cubed times H over B minus A minus A cubed times H over b minus a. And so we're left with 1/3. I can factor out the h, so I guess I'll make it h over 3. Well, actually no. I think I see where this is going, so I actually want to keep it written as 1/3, but let's continue it over here so I actually have more space to work with. So we've got 1/3, and then I'll factor the h out over there. Did I even leave enough space in here? So we've got b cubed minus a cubed over b minus a. And this can actually simplify. We can actually simplify this because it's a difference of cubes. B cubed minus a cubed is, I guess I'll continue it here, 1/3. B cubed minus a cubed is b minus a times b squared plus ab plus b squared all over b minus a times h. Okay, and the b minus a's cancel out. So it's 1/3 times b squared plus ab plus, oh wait, did I write b squared there? No, that's supposed to be a squared. My bad, that's supposed to be a squared. B squared plus ab plus a squared all times h. I mean, this is kind of similar to the normal formula of a pyramid. It has some resemblance to it, because for a normal full pyramid, what's the volume formula that you were taught in geometry class that you've probably forgotten if you're the typical student, because being asked to remember the volume of a pyramid is apparently too much to ask for. I could tell you stories about my classmates in college who didn't remember some essential volume and surface area formulas that we needed to know for physics. Volume of a pyramid that you learned in geometry, at least for a right pyramid, is 1/3 the base times the height. 1/3 the area of the base times the height. And of course, in this case, our base area is the area of a square, so I guess you could write this as 1/3 s squared times h. So yeah, it has some resemblance to it. I mean, you've got 1/3, I guess you could say b is one of the bases, and b squared is the area of one of the bases, and a squared is the area of another of the bases, and then that times height. But does that actually make sense? The plus AB part, would that actually make sense? Oh, well, it's not the full height. Okay, the height here is not the height of the full pyramid. The height here is the height of the frustum of the pyramid. Okay, that's what was bothering me. Because I was thinking if this is h, then that would be bigger than the volume of a normal pyramid. But yeah, this h and this h are not the same. This is a different h. Okay, so 1/3 b squared plus ab plus a squared. That's our times h, of course. That's our frustum or pyramid frustum volume. And then it was asking what happens if a is equal to b. What happens if a is equal to b? If a equals b, then this formula would simplify to 1/3. Let's say I substitute the a with b, so that's going to be 1/3 b squared plus b times b is another b squared plus a squared just becomes b squared. So that's b squared plus b squared plus b squared is 3b squared times 1/3 is 1b squared times h. If a equals b, then volume becomes b squared times h. So if a equals b, if we draw that, that's just a rectangular prism. And I guess I should have drawn that as a dotted line, but oh well. If a equals b, then you just have, well, not a rectangular prism, but a square prism. Yeah, you'd have something like that if b and a were the same. Your pyramid frustum would just turn into a brick. And then they asked, what if a is equal to 0? If a is equal to 0, then that just means you've got a regular pyramid. If a is equal to 0, then here's b, and then you keep going until you hit, there is no width here. If a is equal to 0, there's no width at the top. It's just going to be a sharp point. And yeah, at that point, it's just a full-on pyramid, so I would expect the equation to simplify to that of an ordinary pyramid. If a is equal to 0, then let's see. That would be 0, that would be 0, and it would be 1/3 b squared times h. Volume would be 1/3 b squared times h. And yeah, b squared being the area of the square base, that would be the volume of a classic pyramid. Okay, that problem turned out to be more complex than I had anticipated, but I guess that's why it was worth it. And I guess that'll be that for basic volumes. What about volumes by cylindrical shells? What about volumes by cylindrical shells? Let's do an example or two of those. And then move on to something that's not so volume heavy. Let's see, volumes using cylindrical shells. Use the method of cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the given curves about the x-axis. Okay, so this one is a whole set of problems where we're just rotating around the x-axis. Probably should have written it first. Oh well, you know what it's supposed to say. So rotating around the x-axis, we've got, one of them says xy equals 1, and x equals 0, and y equals 1 and y equals 3 are our boundaries. Let's go ahead and draw that and see what we're looking at. So xy equals 1 is the same as if you divide both sides by x, that's y equals 1 over x. So that would look like so. Xy equals 1 would end up looking like this. Then we've got x equals 0, which is this right here. We've got y equals 1, which would be, I guess, here. And y equals 3, so that's y equals 1. And then y equals 3 would be about here. Okay, and that takes care of that. So it looks like the only region that's touching all 4 of those is this right here. And we're rotating this around the x-axis. So we're rotating this thing around like so. Okay, so at first glance it looks like you could try and use the washer method for this. And if you did that, you would just have to split it up into 2 integrals, because for one of the integrals, you'd have to split it around there, because for one of the integrals your outer radius is going to be from the x-axis to y equals 3, and then for the other part it's going to be from the x-axis to I guess y equals 1 over x. So you could do it using the washer method with 2 integrals, but why bother when you've got the shell method that actually allows you to do it all in 1 integral? Let's take a look at what happens if we draw up some cylindrical shells. So I guess our cylinders would be oriented horizontally in this case. So here is one such cylindrical shell. I guess I want to draw... I am kind of starting to regret not drawing this bigger, but yeah, that's effectively what we're looking at. Okay, so that is a cylindrical shell right there. Yeah, you know what? I'm just going to draw a bigger version of this. Because there are some things I want to be able to show a bit more clearly. So let's make... Okay, that looks good. Now then, how do volumes with cylindrical shells work? Understanding the geometry means you don't have to memorize formulas. So these cylindrical shells are supposed to be super thin, and we're stacking a whole bunch of them together to make the volume of some, I guess if I drew this thing sideways, what would it look like? I guess it kind of looks like a volcano. I guess you would get something that kind of looks like a volcano. Yeah, something like that, and then I guess there's a cylindrical hole right in the middle. So yeah, that's what we're looking at, and you can think of it as a whole bunch of these things, but In this image, I've just rotated that 90 degrees. So if we add up the volumes of each of these individual shells, then we can get the volume of this volcano thing. And to get the volume of an individual shell, if they're super thin, then that means this distance right here should be really, really small, which means the inner radius, this inner radius, and the outer radius are out. If this shell is thin enough, then the inner radius and the outer radius should be approximately the same. Which means if I were to cut this thing open, if I were to say cut along the dotted line here and unfold this, then what would I get? If I were to cut and unfold, then I would get something that looks like this. So I'm going to draw it in two stages. Stage one, where you haven't fully uncurled it after cutting. It would look something like this. And I guess you know what? No, let me draw it down here so that it's not obscured by anything I've already drawn. Let's say I draw it here. So you take that cylinder, or shell, and you cut it along that dotted line, and you start unrolling it, and you get something that looks like this. And if you look at that, you can imagine being able to almost perfectly flatten it out. You can imagine being able to almost perfectly flatten it out. And if you do manage to perfectly flatten it out, then what you have is a rectangular prism. What you end up with is a rectangular prism. So if I finish flattening this thing out, then it will just end up looking like that. And we know how to calculate the volume of this thing: length times width times height. Okay, so let's see. So before cutting this thing open, I guess you could call this the height of the cylindrical shell. And what happened to that? Well, that became this. That's the height, which means if you were to perfectly flatten it out, there's your height. Okay, and that would mean then that this right here, after you cut it open and unwind it, that turns into this, which effectively becomes the length. So the length is equal to the circumference, which is just going to be 2 pi r. This is just going to be 2 pi r. Is it r inner or r outer? Well, if this thing is sufficiently thin, then it doesn't matter, because r inner and r outer are going to be approximately the same. So if you make these shells super thin, it's the same radius on the inside and outside approximately. Okay, and that just leaves this. What was this? This was the thickness of the shell, which is going to be just a very, very small change in the radius, dr. Or delta r if you prefer, but you know, if we make them ultra thin, then we would officially call that dr. So dr is either going to be dx or dy, depending on the direction in which you're integrating. In the case of this problem, it looks like our radius is the distance from our x-axis to the region. So distance from the x-axis is determined by y. Y measures your distance from the x-axis, so this dr, in the case of our problem specifically, is going to be a dy. Okay, so our volume, the volume of this thing, dv, is going to be length times width times height is going to be 2 pi r h times dr, which in this case is going to be dy. And the rest is just setting up an integral, so let's go ahead and figure out what our integral should be. If our radius is going to be determined in terms of distance from the x-axis, then we need to then we need radius as a function of y. Wait, does that mean we still have to split it up into two integrals, though? No, it doesn't. Okay, so I want to get, let's see, our radii are just going to range from 1 to 3. Okay. Radii are going to range from 1 to 3. We're going from y equals 1 to y equals 3. And the heights of these cylindrical shells are going to be the distances between this curve and the y-axis. Those are going to give us our heights right here. So that's going to be right curve minus left curve in order to get a positive height. So our right curve, I guess, since we're integrating with respect to y, I want to turn xy equals 1 into x equals 1 over y. So our right curve is x equals 1 over y. Our left curve is x equals 0. So 1 over y minus 0, of course, is 1 over y. So that's 2 pi times our radius in this case is just going to be y itself times our height is going to be 1 over y minus 0 is 1 over y, and then integrated with respect to y. Okay, did I set all that up right? Doesn't hurt to double check. Let's see. Yeah, that all checks out. So y and 1 over y cancel out. How convenient. And the 2 pi is a constant, which we can factor out of the integral. So we're left with 2 pi times... We're left with 2 pi times the integral from 1 to 3 of dy, which is just going to be y evaluated from 1 to 3, which is 3 minus 1 is 2. So we're getting a volume of 4 pi. We're getting a volume of 4 pi. I feel like I might have done something wrong here, because this just feels a bit too simple. Oh well, I guess when reviewing the video later, if I do notice a mistake, I'll point it out in a pinned comment, as is tradition on this channel by this point. But yeah, there you go. That's volume via cylindrical shells. If you understand the geometry, you don't have to memorize the formula. Let's take a look at... Looks like next thing we have... Well, the next thing I've listed that's worth looking at is inverse functions. Specifically the derivatives of inverse functions. This tends to trip students up because they tend to overthink these problems. And they tend to rush through these problems is the other thing. Let's see, where's the section that had those? The way this book is organized makes it a bit harder to find this particular section. Where are my inverse derivative examples? Okay, here we go. So, for example, let's say we are given a curve, or a function, f of x equals 2x cubed plus 3x squared plus 3x squared plus 7x plus 4. And we want to find f inverse prime of, they want us to find f inverse prime of 4. So what a lot of students will try to do here is that they'll try to find the inverse function and then take its derivative. Good luck doing that with a third degree polynomial or higher. You might be able to pull it off with a second degree polynomial, but not with an x cubed. It's, unless you have some really, really ridiculously simple case, that's not going to happen. So how are you supposed to find the derivative of the inverse then? Well, you can just use the formula for the derivative of the inverse. The derivative of the inverse is equal to 1 over the derivative of the main function applied to the inverse of the function at that same x value. Remember this formula, and if you don't remember it, there's a very, very easy way to derive it. It's actually really, really easy to derive if you know your chain rule and you know the properties of inverse functions. So if f and f inverse are inverse functions, then that means that f of f inverse of x is equal to x. Or likewise, you can also say f inverse of f of x is equal to x. Don't need that there. I think I want to start with this one. Yeah, I want to start with this. So if I differentiate both sides with respect to x, what do I get? Derivative of x is 1, derivative of f inverse of x, that's going to be a chain rule, so differentiate the outer function first, f prime of f inverse of x times the derivative of the inside times f inverse prime of x, which I did not leave enough space for, apparently. Okay, so f prime of f inverse of x times f inverse prime of x equals 1. Divide by f prime of f inverse of x, and you get this expression. Really, really easy derivation, assuming that you're good with your chain rule. Okay, so tangential topics aside, how would we figure this out? So f inverse prime of 4, f inverse prime of 4 would equal 1 over f prime of f inverse of 4. you may not be able to find f inverse of x in general, but you might be able to easily calculate f inverse for specific values. It's pretty easy to figure out what f inverse of 4 is just by looking at this. What x do I have to plug in order for f of x to be 4? I think you can tell it's 0. It's usually going to be something simple like 0 or 1 or -1 whenever they ask you something like this. It's really easy to just look at it and see it. Otherwise, they wouldn't be asking you. So when x equals 0, f of x equals 4. Therefore, f inverse of 4 must be 0. Okay, that solves part of the mystery. So it equals 1 over f prime of 0. F inverse of 4 was 0. So now all we have to do is find f prime. F prime of x is going to be 6x squared plus 6x plus 7. X being 0, so that's just going to give us f prime of 0 equals 7, so that's 1/7. Done. So yeah, do not overthink these problems. To find the derivative of an inverse, there is a formula that relates it to the derivative of the original function before you inverted it. You don't have to invert the function and then differentiate. Oftentimes you'll be given problems where you can't do that. You're more than welcome to try and find a general inverse of this. I will wait. Anyway, next problem type that we want to look at. So now it's time to look at integration techniques. Now it's time to look at some integration techniques, starting with what is sometimes called trigonometric integration, which is really just clever u substitution involving trig functions. Actually, before we do that, should we? Nah, let's not. Maybe that'll be like a separate video when the heat's off. But right now we've got an exam coming up in less than a week for some of you. And I think I just passed over the section that I wanted. Okay, here we go. Found it. So how would we integrate something like sine squared of x times cosine cubed of x? This is all about strategy, so if you've done enough of these, then you'll know what to do in the case of sines and cosines. So in the cases of sines and cosines, if you have an odd power of cosine, then you want to save one cosine for not for u substitution, but to use in the result of your u substitution, and then turn all of your other even-powered cosines into sines using the trig identity sine squared plus cosine squared equals 1. A similar reasoning applies if your sine was the one that had an odd exponent to it. And if they both have odd exponents, then let me think here. I think it should be fine no matter which one you pick in that case. But let's illustrate it with this example and see how it plays out. So what I'm going to do is I'm going to rewrite cosine cubed as cosine squared times cosine. So it's the integral of sine squared times cosine squared times cosine. And then I'm going to rewrite cosine squared as 1 minus sine squared. And then I'm going to do the following u substitution. U equals sine of x. U equals sine of x. Du equals cosine of x dx. Okay, cosine of x dx, there's my du. And then all of those signs just become u's. So we get integral of, that's going to become u squared times 1 minus u squared du. Distribute the u squared, and we've got the integral of u squared minus u to the 4th du, which integrates to 1/3 u cubed minus 1/5 u to the 5th plus c, which becomes 1/3, resubstitute for u, and that's sine cubed of x minus 1/5 sine to the 5th of x plus c. So there you go. If you've got a product of sines and cosines, whichever one is odd powered, save 1 power of it for use with the result of your u substitution to get your du, and convert all the rest into the other function using trig identities. And if they're both even, then you would want to use the half angle identities. So if I had something like sine squared times cosine to the 6th, you would want to use the half angle identities. It would get messy algebraically, but it would be quite doable. And if you don't remember your half angle identities, you might want to review them. You might want to commit them to memory. Okay, let's see, what else do we have? We've got the case of tangents with secants. Also has a rather reliable pattern. So let's say, for example, I've got, let's see, this one says, and I might be able to fit it all in here. This one says integrate tan times secant cubed, integrate tan of x times secant cubed of x dx. Let's see, so it looks like in this case the clever choice would be I can convert secant squared. I can split this into secant squared times secant. So then I would have the derivative of tangent, that's secant squared, but do I want to u substitute tangent? Or would I rather u substitute secant? Yeah, I think that would actually be the better strategy. So if I do u equals secant of x, then my du would be secant of x tangent of x. Secant x tangent x. Oh, and that actually works. Okay, that works out fine because I can take a tangent and one of my 3 secants with my dx to get my du, and I would be left with the integral of secant squared, which I know is tangent. Okay, that one's not too bad. So I didn't have to use any trig identities at all in this case. Let's see, it just becomes the integral of take out a secant and a tangent and a dx to form a du, and you're left with secant squared of x. Well, oh, wait a minute. Secant squared of x. Well, I have to rewrite that in terms of u, so that's going to become u squared. And then integral of u squared is 1/3 u cubed, and then from there it's not too hard to figure out. 1/3 u cubed plus c, which is 1/3 secant cubed of x plus a constant. And I guess I forgot my equals signs there and there. All right, looking good. Let's try something a bit more complex, still involving tangents and secants. How about this one that says integrate, it looks like tangent to the 5th, secant to the 4th. Tangent to the 5th, secant to the 4th. So in cases like this one, what would be a good strategy? I haven't actually memorized the rules of thumb. They are actually listed out in my textbook, but if you know what you're doing, you can usually figure it out without resorting to memorization of patterns. It's not every day I have to do these integrals, so there isn't much point in memorizing. Let's see. I could end up with just... Okay, I think I know what to do here. So I can take all but one of my tangents and convert them into secants, and then I'd have one tangent with one secant would give me secant tangent, which is the derivative of secant. Okay, so we're still going to use u equals secant of x here. I can already see that. That would give me du equals secant x tangent x. Though, I guess, if we did use u equals tangent, that can also work. So, alternatively, we could use u equals tan of x and du equals secant squared of x dx. I keep on forgetting the dx is here for some reason. Yeah, I can see both of those working, because if you use u equals secant of x, then you have to take out a secant and a tangent with dx to get your du. And taking out a tangent leaves you with tangent to the 4th, which is an even power, and there is a trig identity for even-powered trig functions to convert them into other trig functions. So we wouldn't be stuck with a tan to the 4th. We could convert that into a bunch of secants, which can then be turned into an expression involving u. We could turn them into a polynomial. In the alternative method, if you use u equals tan of x, then you would have to take out a secant squared from secant to the 4th, which leaves you with another secant squared, and since it's squared, you can rewrite it in terms of tangents, which can then be rewritten in terms of u's, giving you, yet again, an easy polynomial to solve. So Actually, either substitution will work here. Either substitution will work. So let's use both just to show that we get the same result. Well, they're not going to be exactly the same in terms of the literal expression, but they'll evaluate to the same thing. If you put them in a graphing calculator, they'll trace out the same curve. You might have to do some more trig manipulation to prove that they're equal. So tangent to the fifth becomes, well, tangent to the fifth secant to the fourth becomes tangent to the fourth, becomes tan to the fourth of x secant cubed of x. And then we took out the dx with one tangent and one secant, so now it's a du. And we can rewrite our secant cubed as u cubed. As for tangent to the fourth would be secant squared minus 1, right? It's 1 plus tangent squared of x equals secant squared. Therefore, tangent squared is secant squared minus 1. Okay, so then tangent to the fourth is secant squared minus 1 squared. Tangent to the fourth is tangent squared squared, so that's secant squared of x minus 1 times itself, and then times secant cubed of x du, and then that becomes the integral of u squared minus 1 squared times u cubed du, which is, let's see, u squared minus 1, if we square that, then we get u to the fourth minus 2u squared plus 1, all that times u cubed du, distribute the u cubed, and we've got integral of u to the seventh minus 2u to the fifth plus u cubed du, which integrates to (1/8) u to the eighth, so that's 1/8 secant to the eighth of x, minus, that's going to be 2/6 or 1/3 u to the sixth, or secant to the sixth in other words, plus u cubed is going to become 1/4 u to the fourth, which is 1/4 secant to the fourth of x, and all that plus a constant. Okay, and using the alternative method, we would get, I guess I'll try and write it out over here. Using the alternative method, u equals tangent of x, du equals secant squared of x dx. So we would take a secant squared out with dx, leaving us with integral of tangent to the fifth of x times, out of secant to the fourth, if we take out a secant squared, we're left with secant squared of x, and now we have a du. And I guess I want to wall that off too. Okay, so that is the first step in our alternative solution. Secant squared can be written as 1 plus tangent squared, so that equals the integral of tan to the fifth of x times 1 plus tan squared of x du, And then that can be rewritten where u is equal to tan of x. We can say tan to the fifth is u to the fifth times 1 plus tan squared is 1 plus u squared du. Distribute u to the fifth. That's integral of u to the fifth plus u to the seventh du, which becomes 1/6 u to the sixth plus 1/8 u to the eighth plus c, which is equal to 1/6 tangent to the sixth of x plus 1/8 tangent to the eighth of x plus c. And although they don't look exactly the same, if we did some extra math here, we could prove that they actually are the same, unless of course I made some sort of mistake along the way. But assuming no mistakes were made, these expressions are equivalent. How would I go about doing that? So I can see where my 1/8 secant to the eighth is going to come from if I just replace 1/8 tangent to the eighth. I mean, I would probably end up using this trig identity a whole bunch of times. And yeah, I can sort of see how I would be getting a 1/8 secant to the eighth out of that. But yeah, that's what you would have to do if you really wanted to prove that they are the same. But that's just kind of getting off course for us. So let's move on to something else. I guess we could do cosecants and cotangents, but they function pretty much the same as tangents and secants do. They have pretty much the same pattern. Only difference is a slightly different trig identity. You'd have 1 plus cotangent squared equals cosecant squared would be the identity that you want to rely on, but otherwise the strategies are analogous. So that's trigonometric integration. It's not exactly a new integration technique, it's just clever choices for u substitution when it comes to trig functions. Now let's take a look at trig substitution. Now let's take a look at trig substitution. So let me grab some problems and let's have a look at it. I'm not going to reteach you how to do trig substitution, especially since we're kind of running low on time. I have to be somewhere. Well, I don't have to be somewhere physically, but you know, there's a certain online meeting I need to attend pretty soon, so it looks like this might be our last topic or second to last, depending on how quickly I get through it. And I guess that means there's going to be some more calculus for tomorrow. Or tonight if I have the opportunity. We'll see. I mean, there will be plenty of time on Friday. My schedule is going to be pretty open on Friday. I'll probably do like, I don't know, 6 hours. Let's see. Trig substitution examples. So here they want us to evaluate a bunch of integrals. So let's start with a classic. So we've got integral of, they've written it as dx over the square root of x squared plus 16. All right. So U substitution doesn't work here because if you do u equals x squared plus 16, then you get du equals 2x dx, and how on earth are you going to get your 2x? I mean, if you multiplied by 2x over 2x, you would just end up complicating things even more, and yeah, you would get stuck. U substitution is not the way to go. For cases like this, trig substitution is the best choice. Typically, whenever you see square roots involving your variable squared, that's usually your cue to try trig substitution, or at least consider it. So what I want is x squared plus 16. I want x squared plus 16 to simplify to some trig function squared. So I want it to be equal to a sine squared maybe, or a cosine squared, or a tan squared, or something like that. And with enough practice, you should be able to tell just by looking at the format which one you should try to go for. In this case, I'm seeing addition. So with addition, what I would want to go for is probably secant squared, because I can see x playing the role of tangent squared and 16 playing the role of 1. So yeah, the trig identity that we used earlier, 1 plus tangent squared equals secant squared. That looks like what I'm going for here. When I see addition, I'm trying to make a secant squared or a cosecant squared. Technically, you don't even need to consider cosecant because, how do I say this? Anything that works for cosecant would work for secant when it comes to trig substitution. Anything that works for cosine would work for sine, and anything that works for cotangent would work for tangent, just to put it in layman's terms. You're welcome to try, but it's not going to make much of a difference. You're just going to needlessly throw negative signs into the mix that could increase your risk of making mistakes. So sticking with sine, tangent, and secant as your options would be for the best. Anyway, I want my x squared plus 16 to become secant squared of, well, I can't call it x because that's already taken, so let's call it secant squared of theta. Okay, that would mean, well, actually, do I want my x squared plus 16 to be secant squared of theta? Not quite, but I want it to be something related to secant squared of theta. I want it to be something relating to secant squared of theta. So first, I need to get rid of this 16. I need to reduce it to a 1, so I'm going to divide everything by 16. X squared plus 16 is equal to 16 times, if I factor it out, x squared over 16 plus 1. Okay, here we go. And I want x squared over 16 plus 1. That's what I want to be equal to secant squared. So I want x squared over 16 plus 1 to be equal to secant squared of theta. And the way to make that happen is for x squared over 16 to become tangent squared. So x squared over 16 would have to be tangent squared of theta. And if I take the square root, then that means x over 4 equals tangent of theta. Or in other words, x equals 4 tangent of theta. Or in other words, x equals 4 tan of theta. Okay, perfect. Now what I want to do is differentiate. So this is kind of the opposite of u substitution in a way. In a way, you could think of it as being the opposite of u substitution, where in u substitution, you would say u is equal to some function of x. In this case, x is some function of, well, it's not u, but it's theta. So yeah, it's kind of a reversal of that situation. So now our dx is equal to 4 times derivative of tangent is secant squared theta d theta. And yeah, that should take care of it. So our integral becomes integral of dx becomes 4 secant squared theta d theta. I guess I'll pass on writing the parentheses for now. Over the square root of x squared plus 16. Well, our choice of x equals 4 tan theta was designed such that the square root of x squared plus 16 would turn into what? Well, x squared plus 16 turned into 16 times that stuff, and that stuff turned into secant squared. So it looks like we've got 16 times secant squared of theta inside of our square root. Yeah, this stuff is secant squared, and x squared plus 16 is 16 times that. Okay, and that leaves us with square root of 16 secant squared. That's, well, square root of 16 is 4, and square root of secant squared is secant. So we've got 4 integral of 4 secant squared over 4 secant. And it looks like this marker is pretty much dead. The 4's cancel out 1 power of secant, and you're left with the integral of secant theta d theta, which you hopefully have learned in class is going to be some sort of natural log. I would recommend committing this one to memory. I mean, it's not too hard to rederive if you know what to do. And actually, I might have to rederive it because I don't remember it. At least I don't think I do. It's integral of secant theta d theta. Let's see, I believe that's natural log of secant plus tangent. Let me do a quick mental check here. If I multiply by secant plus tangent over secant plus tangent, and then u equals secant plus tangent, secant squared plus secant tangent. Natural. Okay, yeah, that's what it is. Equals the natural log of secant theta plus tangent theta. And of course, we need absolute value bars because you cannot take the natural log of a negative. And plus c. So that takes care of it in terms of theta. We need to get it back in terms of x, our original variable. So that's going to equal, I'll continue it over here, equals the natural log of, what is secant theta? So, well, we have a relationship between tan of theta and x, so let's draw our reference triangle. Here's a right triangle, not necessarily drawn to scale. Here's our angle theta, and our angle theta is such that the opposite over the adjacent is equal to x over 4. Okay, let's make the opposite x and the adjacent 4. You don't have to do it this way. You could make the opposite x squared and the adjacent 4x. As long as the ratio between them is x over 4, it'll work, but, you know, go for the easiest thing that's available is my policy on this. But you can do whatever you want so long as you have the correct ratio. Okay, in that case, the hypotenuse would be the square root of 4 squared plus x squared. So 16 plus x squared. That should look familiar. Okay, and from this we can find an expression for secant theta. Secant theta is hypotenuse over adjacent, so it's going to be the square root of 16 plus x squared over 4. Square root of 16 plus x squared over 4. Plus tan of theta we defined as being x over 4, and plus c, and there we go. And of course there are alternative ways you could have expressed this. So I guess another way you could have expressed it is you could have rewritten secant theta as the square root of this expression. Yeah, you could have done that. Okay, so that takes care of one of those. Let's go for another. Okay, this one is marked in red, so I'm hoping it'll be a challenge. Wait, this one... it's pretty much dead. Going to the trash. And let's grab a new color. How about... To get good color variety, I guess I would go for... Let's go for the light blue. Okay, so where was I? Right, this problem marked in red. Hopefully it'll actually be a challenge. We've got, well, depending on who's watching this, it could be a challenge to you. I can't always accurately predict what will be more challenging to students and what won't be. I've had plenty of cases where I expect something to be actually rather simple for students, and for whatever reason they get stuck on it, so maybe I shouldn't be in the business of predicting what's difficult for students and what's not. The curse of knowledge, that's what it is. When you know something, it's hard to imagine not knowing it. And that's why not everybody can teach. Okay, square root of x squared minus 9 over x cubed. So when I see subtraction, I definitely don't think of secant squared or cosecant squared. Now, it depends on whether we're subtracting a constant from a variable or a variable from a constant, and it looks like we're subtracting a constant from a variable here. So I wouldn't want to go for sine squared. Sine squared is 1 minus cosine squared, a constant minus a variable squared. Your trig function should replace the variable. So that's not going to work, so I would want to go for, it looks like, tangent squared. I would want to use tan squared of theta is equal to secant squared of theta minus 1. So I want to get x squared minus 9 to look like secant squared of theta minus 1. And the first step is to factor out a 9. X squared minus 9 equals 9 times x squared over 9 minus 1. Okay, x squared over 9 minus 1 can become secant squared of theta minus 1. So x squared over 9 is going to become my secant squared of theta. And if I take the square root on both sides, I get secant theta is equal to x over 3. Okay. X over 3. So in other words, x equals 3 secant theta. And if I differentiate, then I get dx equals 3 secant theta tangent theta d theta. All right, I think that's everything we need. Let's go ahead and make our substitutions. Integrate, let's see, square root of x squared minus 9. So this stuff became secant squared of theta minus 1, which is equivalent to tan squared of theta. So I've got 9, or the square root, I should say, of 9 tan squared of theta. Dx becomes 3 secant theta tangent theta d theta. And then x cubed. X cubed is going to be, well, x is 3 secant theta, so x cubed is going to be 3 cubed is 27 times secant cubed of theta. Okay, we've got some simplifying to do. So square root of 9 tan squared theta is just going to become 3 tan theta. So we've got 3 tan theta, and then times 3 secant theta tan theta d theta over 27 secant cubed of theta. Let's see, I can cancel out 1 power of secant, so that reduces to a secant squared. And then in the numerator, I've got tangent times tangent will become tangent squared. The 3 and the 3 and the 27 can reduce. That just leaves us with a 3 in the denominator. So I've got tan squared over secant squared. So we've got the 3 in the denominator. I'll factor out of the integral as 1/3. And then we've got integral of tan squared over secant squared. If you know your trig identities, you will not be remotely confused on what needs to be done here. Secant squared is equal to 1 plus tan squared, or alternatively, tan squared is equal to secant squared minus 1. If I rewrite tan squared as secant squared minus 1 over a one-term denominator, this is kind of reminiscent of the problem I showed in yesterday's stream, where you had an algebraic function, not exactly a polynomial, all over the square root of x. I think that was what I wrote. And I noted that if your denominator is a single term, then you can distribute it over all the terms in the numerator, something that students often forget for whatever reason. So I can rewrite this as 1/3 integral of tan squared becomes secant squared of theta minus 1 over secant squared theta d theta. Okay, so secant squared over secant squared is 1 minus 1 over secant squared. Well, that's cosine squared. So we've got 1/3 integral of 1 minus cosine squared of theta d theta. And how do we integrate cosine squared? Integrating 1 is easy. What about cosine squared? More trig identities. More trig identities. So I know that cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta, which is also equal to 2 cosine squared theta minus 1, which is also equal to 1 minus 2 sine squared of theta. In this case, I want to use this one. So if cosine of 2 theta is 2 cosine squared minus 1, then cosine 2 theta equals 2 cosine squared minus 1. Probably should draw a dividing line between those. If cosine 2 theta is 2 cosine squared minus 1, add 1 to both sides, divide by 2, and take the square root, and that's equivalent to... Actually, no need for the square root. Cosine squared will be equal to cosine of 2 theta plus 1, all divided by 2. So, I can say this is equal to 1/3 the integral of 1 minus, if it was all divided by 2, that's 1/2 times, it was cosine 2 theta plus 1, or 1 plus cosine 2 theta, however you want to write it, d theta. Okay, and that is much easier to integrate. So if I distribute the 1/2, 1 minus 1/2 of 1 is just 1/2. So I've got, I guess I'll continue it on another sheet. So we've got 1/3 the integral of 1 minus 1/2 is 1/2, and then minus 1/2 times cosine 2 theta is just minus 1/2 cosine 2 theta d theta. So integral of 1/2 with respect to theta is just 1/2 theta, and integral of 1/2 cosine 2 theta is going to be 1/2 sine of 2 theta over the derivative of 2 theta, which is 2. So let's see here. We would have 1/3 times 1/2 theta minus 1/2, and we're dividing by 2, so that's 1/4 sine of 2 theta plus c. Okay, and rewriting everything in terms of x, let's draw ourselves a reference triangle. So we had x over 3 equals secant theta. That's what we had up here. So let's use that to draw a reference triangle. Okay, so I'll let this be theta, and then secant of theta is x over 3. Hypotenuse over adjacent is x over 3. So hypotenuse, I'll make it x, and adjacent, I'll make it 3. And that would mean that this side is equal to the square root of x squared minus 3 squared, x squared minus 9, which, again, should look familiar. That's what we had in the beginning. That's what you should expect to see with these problems. That's kind of another one of those, I guess you could call them tells that let you know if you've made a mistake. So that's another thing to be on the lookout for. If you don't get something that looks like what you had in your original integrand, then that tells you that something went wrong and you need to do a double take. Or maybe nothing went wrong, but either way, double check to see. That would be a good motivator to double check your work. So we've drawn our reference triangle. We can use that to evaluate, or well, not evaluate, but rewrite this in terms of x. I'm going to go ahead and distribute the 1/3 over everything, so we're going to get 1/6. And then what is theta? I guess you can just define theta as a secant inverse of x over 3. You can just define it as secant inverse of x over 3 based on the substitution we wrote earlier. So that's going to be secant inverse, or arcsecant if that's how you prefer to write it. I guess I'll just write it as arcsecant of x over 3 minus 1/3 times 1/4 is 1/12. And then sine of 2 theta. So some people will just rewrite it as sine of 2 times arcsecant of x over 3, and I guess that's technically right, but I'm a little more adventurous, so I'm going to actually try and find a more algebraic expression for this, which I think I will be able to do. Let's hit pause on this to figure out what it's going to be. Let's do that somewhere separately. I guess I don't need this sheet up here anymore. Okay, that's a bit more comfortable, at least for me. So sine of 2 theta, if you know your double angle identities, sine of 2 theta is equal to is equal to 2 times sine theta times cosine of theta. Okay, so that equals 2 times, sine of theta is opposite over hypotenuse, is square root of x squared minus 9 over x, according to our reference triangle, times cosine theta, which is adjacent over hypotenuse, or 3 over x. And yeah, there you go. Not too bad at all. So I can replace sine of 2 theta with, 2 and 3, 2 times 3, those are going to reduce with the 1/12. 6 over 12, that's just going to reduce to 1/2, so I'll scribble out the 1. So now we've got 1/2, and then the rest is square root of x squared minus 9 over x, and x just becomes x squared. And there we go. So I can see why they marked that one in red. It did pose a bit of a challenge. And yeah, that's the gist of trig substitution. You've seen it before, but the more practice you get, the better you'll get at it. Okay, and I guess that's where we will have to end it for today. So it looks like we will be doing even more calculus tomorrow, more integration techniques, and maybe a little bit on series before we move on to physics. Yeah, that looks like the plan, so look forward to it. Let me think, is there anything else I want to say before calling it a day here? Well, in case you missed it, or you're the type that doesn't read the descriptions on videos, I did post links to some of my old physics videos and my chemistry videos in the description of the last stream, so if you're looking for something to keep you busy until I actually get to covering physics, that's where you can find that stuff. And yeah, I think that's the only thing I wanted to remind of, so that'll be it for today. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I will see you tomorrow.